and then move on to the next talk, which is by Joshua Peak of SDSCI, who will talk to us about the Hubble Image Similarity Project.
Hi, I'm Josh Peak. I'm presenting today on the Hubble Image Similarity Project, which is a lot of work done at Space Telescope Science Institute, largely by myself, but also especially Rick White. And I'm putting ADASS here with non-Roman numerals because I don't understand why we use Roman numerals in a place we care so much about data standards. Okay, moving on. So how do we find data in an archive? That's a generally interesting question to me since I'm the PI of the Mikulski Archive for Space Telescopes here at Space Telescope Science Institute. And usually what we do is we look by camera filter, exposure time, PI, metadata, things we knew about the image before we took the image. One way we've solved this problem of looking for things that we actually took pictures of is making catalogs, just like you heard in this previous talk. The catalogs contain some kind of metadata about the individual objects, magnitude, position, morphology, opticity, Sersic index, etc. But we were trying to answer a harder question. Let's say I have a complex image, like the ones that are behind me in my virtual background, that have lots of structure in them. How do we find, an image that's similar to a flocculent edge-on galaxy or some kind of shock we're seeing, an interstellar absorption cloud? How are we going to find things like that? So in ADASS 27, I gave a talk about a search by image method using convolutional neural networks. Let me explain how that method works, since maybe you weren't all at that meeting and heard that talk. We basically took an image. In this case, our test image was this Magic Mountain image from HST. We cut it up into little tiny pieces, and we fed it through an existing convolutional neural network that has been trained already on terrestrial images, the famous ImageNet data set in this case. This is ResNet 50. There's lots of networks you can use. And then we get these sort of stubby feature vectors. So as you all know, the interstellar medium is about 10% velvet by mass, and then it's 6.4% stingray. Of course, this isn't true, but it does give you a sense that this network is learning something about what's going on in each of these images. We then take these very stubby feature vectors, none of which have a length close to 1, because none of them are actually detections of velvet or binder or gene or stingray, and we cluster them, in this case using t-SNE, although that's we can change as well. And what we find was a really nice result, which is that if you select one of these points in this t-SNE space and you ask what is near me, well, that point corresponds to that red box there on the left, and you can see it's the edge of a photodissociation region, and we're finding the things that are near it, and these yellow boxes are also edges of photodissociation regions. So that's a good sign that this method is working, and that's what we presented in this paper you can read from ADASS 3 years ago. Since then, we've tried this on 20,000 ADASS previews, and we have sort of a prototype system. I'm just showing you a bit of a view of this internal system where we are able to look in different pieces of this space and snoop around. But what we ran into in building the system, it works, it seems to be doing kind of what we expect, is how do we measure and optimize this method? Okay, this is a method that's trying to say, I've given you an image, I've selected an image, I want to see what's similar in your database to this image. I want to find similar things. But and yes, it seems to be working at some level, but how well? Which network should we use to do this with? Of choices. What parameters should these networks be trained on? What settings? Maybe there's some totally different method that somebody proposes, and we don't know if it's better. We need to know how well this method works. So what we need is a sample of images with known similarities, so we can test and improve our algorithms. So that's where the Hubble Image Similarity Project comes in. So the idea is to create a large database of similarity information between segments of Hubble images. We're using Hubble here because we're really familiar with it. One could easily do this with lots of different kinds of telescopes. Hubble images have lots of detail, of course, so they're a nice choice. We turn this into a citizen science project. We employed people in the service industry very close to Space Telescope Science Institute here in Baltimore, Maryland, who were impacted by COVID-19. There's a really nice fit here where people need to be able to work from home. And they need a fair wage, and we can provide that because we need their eyes. So the way the system worked, we selected a wide variety of images, and we thought that NGC objects would be a nice thing to choose from, because as you can see from once again behind me in my magical virtual background, there's lots of different kinds of NGC objects, galaxies, nebulae, star clusters, you name it. And then we took cutouts of a reasonable size that had enough detailed information but weren't enormous, and ended up with about 2,100 image cutouts to compare. So this is my virtual background. You can see that there's a really broad range of these kinds of things, from little clustered, it's just star fields, to the centers of galaxies, to nebulae of various kinds, Bach globules, dust lanes, all sorts of complicated stuff that are very hard to classify in any kind of coherent way, even for professional astronomers. It's going to be, each image will be kind of a mix of different things. So the way we did this is we would basically show the participant a comparison image, and we would ask to say, which images do you see that are similar or most similar to this image? And we did this in 3 stages. So in the first stage, we're just comparing every image to every other image, and just saying, which ones even look vaguely similar. In the second stage, we use the information from the first phase here to say, we're going to take all these different images, we're going to use the ones that are already close pairs, and we're going to find the most similar image. And then the last one was a very high level of refinement, where we're also rotating the images to make sure we're not just being fooled by the orientation of the telescope. So this is what a phase 1 review might look like for one of these citizen science folks. On the left side is the comparison image. We replicated it twice so that it was easier to compare on the screen. And you can see that they're allowed to pick sort of as many ones they think are sort of vaguely similar as possible. And then finally, this is what phase 3 would look like. You've got a comparison image, and it's much harder. You can see all 3 of these images look quite similar in some way. Thanks. This was designed for community impact. As I said, this is trying to employ service industry professionals in Baltimore, waiters, yoga instructors, lots of different people. And we designed it to pay a fair wage. We use the Amazon Mechanical Turk system. I don't know about your institutes, but it's very hard to hire 50 people kind of like that. We started this in March. We were working by April. We were done by August. So there's a really nice article in Wired if you just type Sersic goals Wired. And this is a really great article, both about our project, but in general about citizen science projects and astronomy. So you can nice interviews with people who worked on our project, our neighbors. So we did almost 1 million reviews of 5.4 million pairs. That allowed us to build up a similarity distance matrix between all pairs, so a 2100 by 2100 matrix. We can use that to construct groups and to construct dendrograms, and also to try to figure out the closest pair, and basically make a hierarchy of pairs between every single one. There's some fun ways one can work with these data. The idea is to publish all of this publicly so people can use it to train their own networks, to train their own systems, to test their own systems, and just to use in general across machine learning. It's a really interesting data set. And we can use the results to assess the accuracy of algorithms for our search by image functionality that we're going to be moving forward with at MAST. Hopefully I'll present about that someday when it's ready for prime time. And it's also worth, these data are quite rich, and they may actually be useful in even some level of lightweight training. Mostly we're thinking about them for testing, but they can be useful for training. I'll just quickly show you here a little notebook we have. I hope you can still see my screen. Where this is the result of taking not the network's output, but the output of the users and clustering them. So each one of these points is an image. And if I click over here, what I get is the image that I clicked on is over here, and then all the images that are most similar. So here you're just looking at a pretty boring group where people are saying, yep, these are kind of star fields, maybe with some gradients. As we move over here, we start to see lower density gradients, lower density star fields, then maybe a bright star pops up as we move over to here. So you can see there's a really nice grouping here of continuity. We jump over into this region and you get into the interstellar medium. You can see places that have very bright linear features. You can see places where there are opacities here at the edges of photo dissociation regions. If I jump over here, we're now looking at little star forming regions. Sorry? Star forming regions. I'm almost done. And then as we move over here, you can see that this space is just really fun to explore. But you can see, these folks who really don't have any astronomical background in their work, about 30 people from the community, are doing an incredibly good job at putting similar images together. These are flocculent spirals with really nice thin dust lanes. I mean, I can keep wandering around in this space, but I think you've got the impression of what's going on as we wander over this way. We start to get to galaxies that are that have cores that are elliptical cores and bulges and so forth. So this is a pretty neat demonstration that what these folks are doing is really useful, and that this will really be helpful in testing out our algorithms. So maybe I will stop there and take questions.
Thank you very much, Josh. We have one question in the Discord, which is, great idea to pay a fair wage to people who help, especially in this pandemic. Can you please elaborate on how much that is per hour of work, per number of classifications made? Thanks.
Yeah, we aimed, it's a little hard because Amazon Mechanical Turk is designed by the task. And so we tried to work pretty carefully to get it in the right, to fine tune it. So we got to about $20 an hour, which, in consultation with folks here in the industry, that would seem like a reasonable wage for this work.
Henrique asks, are the people who selected the images eligible for authorship and eventual publications?
That's a great question. I'm going to be reaching out to them as we move forward with this, and I'd love to get their input. I certainly would like to acknowledge those people one way or the other. I'm not sure if that, what's the word? That's the kind of value that they're looking for, but I would be very happy to have these people as co-authors. They're all really great, and it's been a lot of fun working with them. Actually, what I'd like to do is talk to people who've done citizen science work, Chris Lintod and the world of the Zooniverse, and ask them how they've done that and what they've learned from that, because there's a lot of knowledge there that I would have. So if you have thoughts on that, please reach out.
Mark Taylor asks, how much guidance of the work is get about what counts as similarity, e.g. rotation, Great Wall, W.
Right. Sorry, I didn't quite catch the whole question, so I'm just going to pop over to Discord to make sure that I can understand it best. But
my internet.
Yeah, exactly. So yes, we gave them some instruction. We had a couple of Zoom sessions to begin with.
Yeah, about what
I'm not sure if it's me or you, but I'll just speak. The answer is we had a few Zoom sessions with them to answer questions, and we were always available. We got a bunch of emails from certain people early on in the process where they said, okay, I see this and this. Did those count? Does that not count? And we, there were moments where like, oh yeah, okay, so you're getting a little confused by orientation or what have you. And so we found that those kinds of conversations were really useful. This is a really good reason why doing this with people and hiring them, rather than just saying we're gonna pay the lowest possible wage and just get random people from the internet is pretty nice, because you get to work with them. I know there's also citizen science projects that are on platforms like the Zooniverse where there's lots of conversation. So we found those kinds of conversations really helpful.
So I'm just going to ask my own question, which is, so Hussein Tomarian at the CDC was working on this, and he basically has come up with the exact same results with you using self-organizing maps, I believe it was. The question is, like, how do you feed that into the search engine? Like, people who like pictures of globular clusters might also be interested in this other, and that was sort of.
I mean, I think what we want is a system where either you say, here's my image, here's my Edge-on flocculent galaxy or something, find me things like this. So that kind of thing, or, draw a selection box in an image that's already in the archive and then say, find me things like that. The Amazon, like, ooh, I'm Clippy and I want to tell you that you want to find this. I think astronomers know what they want. We have to make it, there's always a culture change question. How do we help people know that this service exists? But I think it's pretty clear that we want to say, bring your own image or select a piece of our image and we'll help you find things that look like it.
Shabir asked in Discord, some of the data points images after feature reduction when clustered are intertwined with each other, like the orange and gray dots. Not sure that the example helped. How are these images differentiated with each other?
Good. So the coloring of the dots comes from a dendrogram analysis, which is to say you have some complex set of, this is like that and this is like that. And then the dendrogram tries to say, we put them into groups. And we know that that's not necessarily reasonable, right? You can have an image that has, I don't know, some nebulosity, but also has an ellipsoid. And so it's going to be like ellipsoids and like nebulosities. And so the idea that it's in a group is sort of ill-posed. So this coloration is just coming from that. It's just, the way the dendrogram works. I don't think we need to use the dendrogram analysis because we're not actually trying to cluster the data. We're just trying to say, A is like B and B is like C and C is like D. So if you give me some new image, I'll just tell you the ones that are most similar to it. We don't have to do clustering because I don't actually need to be told that there's a group of thing called galaxies and a group of thing called, molecular clouds. I already knew that.
The last question is, do you have examples of scientific application of the search by image similarity feature?
Sure. At least for me, as somebody who studies the interstellar medium, I'm really interested in scalloping in shocks. And I know of one cloud that has this kind of scalloping, but man, it sure would be nice to know that, if I was going to go point some big fancy telescope at all the scalloped shocks that exist, I'd like to know that I'm looking at a big chunk of them, or at least to find some new ones. So to me, these kinds of tools are really helpful for trying to do follow-up analysis, where you're trying to say, look, I want to have at least 3, 4, 5 examples of this kind of thing that I'm after, that has some kind of structure to it. So to me, that's a really interesting use case. I think it'll become even more powerful as we expand. We have higher and higher resolution images, especially from space, across larger and larger areas of sky. So think Euclid, think Roman.
All right, well, I think that's all we have time for. In fact, we've gone a bit over, so let's thank our speaker by mechanical applause again.